In the Bohr model of the hydrogen atom, the ground state of hydrogen consists of a proton encircled by an electron with a separation of 5.29 times 10 to the negative 10 to the negative 11th meters. That's the distance between the electron and the proton. Oh, they show it to us there. How lovely. However, since the same magnitude force that acts on the electron also acts on the proton, that would be by Newton's third law, the proton will also move in a circular orbit, but with a much smaller speed and a much smaller radius. Note that the period of revolution of the two particles is the same. That's going to be important to us also. The diagram at right is not to scale because the proton's orbital radius is insignificant compared to the electron's orbital radius. So in this problem, we get to use some of what we learned in Physics 161, which isn't going to happen very often in this course, but we'll enjoy doing that for some of the problems in the electric force section. In part A, we want to know what the magnitude of the electric force acting on the electron is. So for this, we're going to use Physics 161. I want the magnitude of the electric force. I know the force is equal to the charge times the electric field at the location of the charge. I'm looking for the electric force on the electron. So first I find the electric field at the location of the electron. The electric field is equal to K times Q. Q would be not the electron, but the other charge, which is a proton. So this is the electric field at this location from all the other charges, which is just the proton, divided by this distance. Let's call this distance d. So this would be divided by d squared. And let's not make it a vector because it says the magnitude of the electric force. So that's the magnitude. It would be pointing from the charge to the point of interest. It would be pointing like this at the moment that the electron is here. Then we take that and we multiply it by Q in order to get the force. So we would really multiply it by negative E if we wanted to get the direction. But we're just looking for the magnitude, so we'll do the absolute value of the charge, and that will give us the magnitude of the force. So just multiplying it by E gives us KE squared divided by D squared. Then let's put in some numbers. So this is 9 times 10 to the 9th newtons meters squared per coulomb squared. E is 1.602 times 10 to the negative 19th coulombs. We square that now because we're looking for the force. It's charge squared, divided by d squared, which is 5.29 times 10 to the negative 11th meters. And that gives me 8.25 times 10 to the negative 8th newtons. That is the magnitude of the force on the electron. Again, because it's the magnitude, we just use the absolute value of the charge. Assuming the electron travels in a circular orbit around the approximately stationary proton, what is the speed of the electron? Well, okay, pretending the proton is at rest for now, if the electron is going to move in this circular orbit, there must be an acceleration pointing in towards the center of the circle. And the magnitude of that acceleration is v squared over, let's call it capital R. So when you have circular motion, you must have acceleration pointing in towards the center of the circle. And if the electron's moving at a constant speed, that would be all the acceleration we have. We wouldn't have any acceleration in the tangential direction. And the magnitude of that acceleration is v squared over r. So that comes from Physics 161. And if you don't remember that, well, you might need it for other problems in this section. So it's there for you. Might want to write it down somewhere. But it probably won't come up again in this course outside of the electric force section. No, wait, it probably will. Okay, so maybe you want to write that down somewhere if you don't remember that. Okay, so we want to know the speed of the electron. Okay, so I have an acceleration, and from physics 161, what can I do with an acceleration and a force? I can use Newton's second law, which says the net force is equal to the mass times the acceleration. Ignoring the force of gravity, which it is safe to do, we only have one force acting on the electron, and that is the electric force. So I have F net is equal to the mass of the electron times the acceleration, which is the acceleration there. The net force is the electric force. Let's just put in 8.25 times 10 to the negative 8th newtons. The mass of the electron, if you don't know it, it should be on the back cover of the textbook, or the last page in your textbook. It's 9.11 times 10 to the negative 31 kilograms. So this is 9.11 times 10 to the negative 31 kilograms. And the acceleration is v squared. I'm looking for v. Divided by r. That's the distance from the electron to the center of the circle. Which, if we're treating the proton as approximately stationary, we're just going to say that distance is 5.29 times 10 to the negative 11th. But that is an approximation. Okay, so then I have to solve this for v. You can do that on your own. You'd have to bring the other two terms over here and then take the square root, and you should get 2.19 times 10 to the 6th meters per second. So you can check that on your own if you feel compelled to do so. Okay, and then we want to know the period of the electron's orbit. Well, it's easier for me to think of things this way. If the electron's going in a circle, and I want the speed is the distance it travels. If it goes around a circle, that would be 2 pi r for the distance it travels, divided by the time it takes to go in one full circle, which is what the period is. We use a capital T for the period, which means the period is equal to 2 pi r divided by v. So that's the way that I remember it. And so this is 2 pi r is equal to 5.29 times 10 to the negative 11th meters. And v we just found up here, that's 2.19 times 10 to the 6th meters per second. The period should have units of seconds, and you can see here that it does. And this gives us 1.52 times 10 to the negative 16 seconds. Okay, and then in part D, we want to know what is the radius and the velocity of the proton's orbit. They give us a useful piece of information here. So the period of revolution of the two particles is the same. So we're going to do this over here. The period is the same. So I have 1.52 times 10 to the negative 16th seconds, which is the period for the proton. The period is 2 pi times the radius divided by v. But this is the radius for the proton, and this is the speed for the proton, which I don't know yet. So I'm going to use this, and I'm also going to use Newton's third law, which says that the force that the proton exerts on the electron has the same magnitude as the force that the electron exerts on the proton. So that force, 8.25 times 10 to the negative 8 newtons, is equal to the mass of the proton times the acceleration of the proton. And the acceleration of the proton, if the proton is moving in a circle at a constant speed, that acceleration is going to be directed towards the center of the circle, which, hey, look, that happens to be pointing towards the electron at this moment. So towards the center of the circle, and also towards the electron, because it's the electron that exerts the force. And it's the mass. The net force is equal to the mass times the acceleration. The acceleration, because it's uniform circular motion, is v squared over r, but it's the radius for the proton and the speed for the proton. So now you can look up the mass of the proton in the back of the book, or on the last page of the book. It's 1.67 times 10 to the negative 27th kilograms. And we have two equations here. And if I know the mass of the proton, let me just say that's 1.67 times 10 to the negative 27th kilograms. So I have two equations and two unknowns. So I can solve for one of those unknowns, and then I can solve for the other unknown. So I have a VP squared divided by RP in this equation. I have a VP in the denominator here, the radius of the proton in the numerator. I'm going to take this and solve for VP divided by RP. So I'd bring those over to the other side. This would be equal to 2 pi divided by 1.52 times 10 to the negative, is that a 16? Yeah, that's a 16. 10 to the negative 16 seconds. I actually did it the other way when I calculated it before. So this is 1 over 2.42 times 10 to the negative 17 seconds. Okay, and then what we're going to do here is we're going to say this is equal to 8.25 times 10 to the negative 8th newtons, 1.67 times 10 to the negative 27 kilograms, times, I only have one v here, so I'm going to say this is the velocity times the velocity divided by the radius, and then I can take this and I can put it in here, and then I can solve for the velocity. So bring the 1.67 times 10 to the negative 27 kilograms over to the other side by dividing by it. So this is 1.67 times 10 to the negative 27th kilograms. And then I had a VP divided by RP. If I bring it over to the other side, it's RP divided by VP. RP divided by VP is 2.42 times 10 to the negative 17th seconds. You can pause the video if you need a little time to go through that on your own. And assuming that I did everything correctly here, I get 1,196 seconds, which rounds to, this is supposed to be a velocity. A newton is equal to a kilogram times a meter per second squared. Kilograms are going to cancel out. One of these seconds will cancel out with one of those seconds, and that will be meters per second. And let's check in the back of the book. So mathematical analysis 7, so I look at number 7, they have 1200 meters per second, that rounds to 1200, so that's good. And then if this is the velocity, now I can use this equation to find the radius. So the radius is equal to the velocity times 2.42 times 10 to the negative 17th seconds. And that should give me, I might have rounded a little bit when I did this, but something like 2.89 times 10 to the negative 14th meters. This is an answer, and this is an answer. If we check in the back of the book, they say the radius is 2.8 times 10 to the negative 14th meters, so that looks good. Okay, so that's problem 30. We had to use a little bit of Physics 161, and that's what we get. And you might have to use some of Physics 161 in the homework, but whatever you have to use from Physics 161 in the homework, you should see it in lecture first.